Okay, so we're going to identify all the functional groups in this drug Tamiflu, which is an antiviral drug used to treat the common flu. So if we look closely at the structure here, I have a CO2, which means I'm going to have a CO2 here. And this is to an ethyl group, so this makes this an ester. Carbon-carbon double bond is an alkene. NH2 is an amine. This guy here, C double bond O to an N, is an amide. And then I have a COC, this is an ether. Alright, so this problem is asking us to convert the ball and stick into the skeletal structure and then identifying the functional group. So the first one is methyl anthranilate. This is in neroli oil, which is a fragrant oil that comes from bitter orange tree that's used in the perfumes. So if I look at the carbon structure here, there's a 6-membered ring with alternating double bonds, and we don't have to draw the hydrogens in. If I look at this group here, there's a carbon that's double bonded to an oxygen. There's another oxygen and the CH3 group, and then I have an NH2 here. So the blue represents nitrogen, and red is oxygen. So the functional group with the carbon double bond oxygen to the R group, this is an ester. This is an amine. And the ring part of this here is the benzene ring. So there's the amine, and this is an ester. Okay, to draw L-amycin, this is in nutmeg tree and gives other flavors and fragrances. This one also has that same benzene ring. There's a carbon and the double bond here, and then I have down here an oxygen to a CH3 group. Here's another oxygen to a CH3 and another oxygen to a CH3. So those 3 OCH3 groups, those are all ethers. And this here is an alkene. And then we have that same benzene ring. There's different properties that we'll encounter with functional groups. The way that they interact with themselves and each other will affect bonding, their physical state, melting points and boiling points, and also solubility in water. If we look at an organic compound, this one is for butane, which is shown there. You might encounter butane in a lighter. Those are covalent bonds between each of those carbons and hydrogen. This one happens to be a gas at room temperature. It has a low boiling point of negative 0.5 degrees Celsius. And the melting point is also low. It's negative 138, which is why it's a gas at room temperature. These are not soluble in water, but they are soluble in organic solvents. And as we know, because we use them in lighters, it's very flammable. Then there's sodium chloride, which is an organic compound. This is found in table salt. The bonds in sodium chloride are ionic. It's solid at room temperature. The boiling point of this one is very hot, as is the melting point. This one is soluble in water because it's an inorganic compound. It does not have carbons and hydrogens, and so is not soluble in organic solvents and also is not flammable. When we look at electronegativity of compounds, that is the measure of how particular an atom wants the electron density in a bond. Some elements will want electron density more than other ones, and that will depend on their polarity. The polarity of an atom depends on the electronegativity of the atoms that form it. In a nonpolar covalent bond, you have 2 atoms of identical or similar electronegativity that are joined together. So for example, a CC bond would be nonpolar, and a CH bond is also considered nonpolar. In a polar covalent bond, we're going to have atoms of different electronegativity that are joined together. So examples of this include a CN bond, a CO, or a CX. Polar bonds are usually indicated with these delta positive and delta negative, where this is the nonpolar end and this is the more polar side. So that partial negative denotes the more electronegative atom. So En is for electronegative. So in a CN, the carbon is more electropositive, and so that gets the partial positive sign. The nitrogen is more electronegative, so that gets the partial negative, and the same thing with the halogen. So carbon is usually at the positive in the covalent bond, and the halogen is going to be the partial negative. So we're going to add another definition here, or something extra. This is uneven sharing of electrons. Here we can use the partial positive and partial negative to indicate where our polar bonds are doing. So this is partially positive, that carbon is, and oxygen is going to be partially negative. So that's formaldehyde, which is a preservative. Chloroform used to be used as an anesthetic before they found out that it actually could kill people in too strong of doses. So we can use the halogens here, the chlorines are partially negative, and our carbon is partially positive. And then we have methamphetamine, which is an illegal addictive stimulant. The nitrogen is partially negative, and these flanking carbons are partially positive. Hydrocarbons in general are nonpolar. If the individual bond dipoles cancel in a molecule, the molecule is overall nonpolar. So if we look at ethane, we have 2 carbon-carbon bonds and then 2 CH3 groups. So this is a symmetric molecule. One end is going to cancel the other out, so this is nonpolar. And then for chloroethane, if I swap one of those hydrogens with this chlorine, that's going to make it partially negative, and we can't cancel one out because it's not symmetric. The polarity is going to favor one direction, so this is a polar molecule. So in this case, the individual bonds don't cancel out, so the molecule is polar. If we look at dichloroacetylene down at the bottom, we can draw partial positive, partial negative here on both sides. But because the chlorines are pulling those carbons equally apart from each other, those cancel each other out. And it's also symmetry. It's also symmetric, so that one's going to be nonpolar. And then with methanol, there's polar bonds here. H has a different pole than the CH3, but that oxygen and those electron lone pairs here have a pole as well. So the net dipole is going in this direction up. So this is a polar molecule. So in this problem, we're looking at dichloromethane, which is CH2Cl2. And we need to explain why this is a polar molecule. So this is used in paint remover. If I draw out CH and a Cl, I know that chlorines are electronegative. If you want to draw in all those lone pairs, you can, just to show that. So the net dipole is in this direction, so that's why this is polar. So one of the things that you want to avoid doing in problems like this is drawing the Cl's this way and thinking that this is going to pull apart and cancel each other out. But you want to remember that the molecules can rotate around, and they're going to rotate so that the like particles are on the same side. And one of the things to remember about solubility, or maybe you've heard it before, is that like dissolves like. And that means that most organic compounds are going to be soluble in other organic solvents. To determine whether or not organic compounds are water soluble, there's a formula for that, and it can be water soluble if the number of carbons divided by the number of nitrogens plus oxygen is less than 4. So if the number of carbons divided by the number of nitrogens plus oxygens is less than 4, then it's going to be water soluble. If we take a look at ethanol, there's 2 carbons and 1 oxygen. This equals 2, which is less than 4, so this one is water soluble. This compound, cholesterol, if I counted up the number of carbons, there are 27 carbons divided by 1 oxygen, which is greater than 4. This is not water soluble, which is why too much cholesterol in our blood is not good for us. We can predict the solubility of acetic acid, which is CH3CO2H. This is right here, acetic acid. And then oleic acid, which is a fat that can be used for salad dressing. So it's a fat that is also an oil. And you might be able to do this problem without even doing the math here. Acetic acid is in vinegar. This is vinegar, and then oleic acid is in oil. And you probably know that when you mix oil and vinegar together, they separate because one of these is water soluble and the other one is not. So vinegar has 2 carbons to 2 oxygens, so this is water soluble. There's 2 oxygens here for many more carbons, and this is not water soluble, which is why our salad dressing doesn't mix together very well. Okay, if we look at how organic compounds can affect the environment, we have a compound that's called MTBE, which stands for tert-butyl methyl ether. This is one used as a high-octane additive in unleaded gasoline. It's not toxic or carcinogenic, but it is water soluble. So there have been small amounts that can contaminate drinking water. So that's where we might see some of these as pollutants. We also have PCBs. PCBs are polychlorinated biphenyl compounds, and you can see up there we have 2 benzenes here that are connected with different chlorine groups. There's lots of different types of PCBs. These are used in the manufacture of polystyrene coffee cups and other products. They get released in the environment when they're being made, when they're being stored, and also disposed. These are very insoluble in water, but because it's an organic compound, it becomes very soluble in fatty tissue. So animals that eat this gets absorbed by their fat in fish and animals around the world. And so if you are eating a lot of fish that are high in these PCBs, it can slow growth and memory retention in children. Vitamins are also organic compounds. These are needed in small amounts for normal cell functions. You can see the list of different vitamins there. There's 2 types of vitamins, some that are fat soluble. That means they dissolve in organic solvents, but not in water. And fat soluble vitamins have a lot of nonpolar carbon-carbon and CH bonds and a few functional groups. These ones can be problematic. So if you consume too many fat-soluble vitamins, your body doesn't have a way to get rid of them. And so they get just stored in your fat, which may not be a good thing. Water-soluble vitamins such as vitamin C will dissolve in water, and these have a lot of polar bonds, and if you have an excess of those can be excreted. Your body is 70% water, which is why water-soluble vitamins can be excreted. The liquid is made up of blood, urine, different gastric juices, and these can dissolve ions, so different sodium and potassium. Vitamin A is one of the vitamins that we get that is not water soluble, but it is fat soluble. Beta carotene can be converted into vitamin A, and that's what we get from carrots. So some of the stored beta carotene reaches the surface tissue of the skin, giving you an orange color if you consume too much of it. And that's not water soluble, so that's why it gets stuck there in your skin. If you eat too much vitamin A, that can cause headaches, loss of appetite, and possibly even death. Vitamin C, which is also known as ascorbic acid, is water soluble. You can see all those carbons to oxygens. This is important in the formation of collagen, and deficiency in vitamin C causes scurvy, though this is not a common ailment anymore. So vitamin A and other fat-soluble vitamins can be stored in the liver and fatty tissue, while vitamin C and other water-soluble ones are soluble in the gastric juices, and those can be excreted through your urine.